Good morning, students. In lecture number 13, we are going to see chapter number 2, that is control and materials of MEMS. So myself, Madhuri Mulik, working as assistant professor in Department of Electronics and Telecommunication, Sharat Institute of Technology, College of Engineering. So in our subject Introduction to MEMS, in the last session we have started the control and materials of MEMS. So from that chapter we have seen substrate and wafers, then why the substrate is used on, then wafers, what is mean by wafers materials, then active substrate materials, in that silicon, germanium arsenide, gallium arsenide, germanium and quartz. Then we have seen the silicon. Okay. Then next, so for today's session, we are continuing that the silicon. So silicon, so already we have seen the most important material which is having the mechanical as well as the electric property, as well as it is elastically also for that the elasticity of the silicon also, that's the important one. So silicon material is best from every point perspective to form the MEMS material or devices. So it is suited for the fabrication also. So let us see the next point with the continuation of the silicon. So the crystalline orientation of silicon is important in fabrication of MEMS devices, because some of the enchant used attack the crystal at a different rate in a different direction. So see this figure, low crystallographic index phase of silicon. So this is, which is plane, we have taken front plane, that is 100. Then for this crystalline structure we have diagonally we have taken rectangle, that is plane is 110, and this is nothing but the triangular diagonal shape which we have seen taken as a 111 plane. Okay, so these are the orientations, and these orientations are very important when fabrication of MEMS. So silicon is dominant as a substrate for MEMS, but research and development is ongoing with other non-semiconductor substrate materials. So silicon means, from the traditional electronics devices, the silicon is the one of the best material and the most common popular material, that the semiconductor material is nothing but the silicon. So in a MEMS fabrication also, silicon substrate is very important. And silicon, when we are thinking related to the silicon crystalline orientation, so 100, 110 and 111, these orientations are very important while we are fabricating the MEMS devices. So with the silicon, the research and development is also working on the non-semiconductor substrate material. So in that, including metals, glasses, cords, crystalline insulators, ceramics and polymers. So these are also non-semiconductor substrate where they are used in a MEMS devices. So the ability to integrate circuitry directly onto the substrate is currently the underlying issue with today's MEMS substrate materials, hence the success of silicon. Means now also, if we replace that the silicon for the integrating the circuitry directly onto the substrate, so that is the biggest task in today's research and development, while we are using main substrate than the silicon. But the silicon having that much success to develop that the other layers on that the silicon substrate. So these are the low crystallographic index planes of silicon. Then silicon crystal orientation already we have seen, but let us see in detail. So each side is tetrahedrally coordinated with four other sides. Okay, each side of that the crystalline structure of the SI. So with other sides in the other sublattice. So more means if you take the equivalent planes, okay, from that the same families. So here that is shown the structure, and here represent in that different ways. So here see this already we have seen the plane. So that is 1 1 1. This one is nothing but the means that the any side. So that the 1 0 0, and this is the 0 1 0. If you see that the orientation from this side, so from the every side we have taken this orientation, and according to that we have say as this is 1 1 orientation, 1 0 0 orientation, 0 1 0 orientation. So here that the much means more atoms per centimeter, that is 1 1 1 1 0. But if you see this first and last one, so this is oxidized faster than the 1 0 0, but etches much lower. So according to the orientation of that, the structure of that the silicon, so whether it is the suitable for the oxidized layer, or whether it is suitable for that the etching layer, so that is that we have to consider by using that the crystal orientation property. Okay, so these crystalline orientation is very important, right? Whether it is the used for the oxidization or whether it is used for the etching. Then next the silicon wafer manufacturing process. So it is very important one, that silicon wafer manufacturing process. So if you see here the 10 steps are shown in the silicon vapor manufacturing process. So already in a previous chapter we have seen that there is a substrate and vapors, two important materials used to fabricate that the MEMS. So what is substrate? This is that the single slice which is formed by using large number of vapors. So on that substrate we are going to fabricate the MEMS devices. So before that means we have to know how to that the substrate is formed. So substrate is nothing but the many number of vapors. Okay, so let us see that how that the vapors, silicon vapors are manufactured. So here that the raw polysilicon. So polysilicon already we have seen it is the purest form of the silicon. So there is a 99.999% the purity. So these we have to first upon grow the crystal. So in this state, this polysilicon seed crystal is placed in this crucible, and this crucible is kept under into the heat. So at the same time there is a one cooling rod is there. So over that means this is heated up to that level, the vapors are formed here. So that vapors are cooled by cylindrical this conveyor part. So single crystal ingot is formed here. So this is nothing but the single crystal. So means what we have done here, the polysilicon seed crystal we have crucible, it is heated up to that the largest melting point where the vapors of that the polysilicon seeds are come or cooled from that the cylindrical, so that single crystal is overcome on this. After this, the crystal trimming and diameter grind is applied here. So flat, after the flat grinding, so we are going to take the vapor slicing from this. Okay, so vapor slicing. So once the vapor slicing is done, after that edge rounding is done over here. Okay. So edge rounding of that is take place. Then lapping of that the edges. Okay, the next step is the lapping of that the edges. So after this, here is any vapors are remaining. So it is etched by using that the chemical solution, and after that it is placed in a slurry to polish the heads of that the vapor. So polishing the after polishing, you will get that means we have to test that the polished vapor silicon. So it is under that the inspection we have to check whether it is there is no any damage on that the single silicon vapor. Okay. So the steps are very easy to understand. First, we have to take that the raw polysilicon seed crystal. It is heated such that the vapors are pulled out from the spindle structure. So this is crystal trimming and diameter grading. From that, the flat grading is then where it is cut into the vapor slicing. So by edge routing, the edge we are going to make correct. Then after the lapping, it is etching process is done. After the etching, polishized it, and after that the single silicon vapor is come, that is under into the inspection. If it is okay, then silicon vapor is formed. So these silicon vapors are used to form that the substrate, and over that substrate we are going to form the MEMS structure. So understood what is the process is applied and for the silicon wafer manufacturing process. Then next is the types of silicon. So following are the types of silicon. So here single crystal silicon, polycrystalline silicon and amorphous silicon. Okay. So using these silicon wafers, that the silicons are made up into single crystal silicon, polycrystalline silicon and amorphous silicon. So next is the single crystal silicon. So the conjoining of IC processing with SI micromachining technique during the 1980s market the advent of MEMS and positioned SI as the primarily material for MEMS, so that it is also called as monocrystalline silicon. Okay, so we have seen the silicon crystal. Okay, so in a previous slide, that is orientation of the silicon. So that the single crystal silicon is formed or micro manufactured in 1980. So that silicon, that the primary material for that the silicon is also known as the monocrystalline silicon. So in a single crystal silicon, single crystal Si has a diamond cubic crystal structure, that already we have seen that the diamond cubic crystal structure. So it has an electronic band gap of 1.1 electron volt. Okay, so silicon crystal having the electronic band gap 1.1 electron volt. So what is band gap? So that is energy gap between the valence band and the conduction band. So after the applying the external supply, that electrons from the valence band cross that 1.1 electron hole and it will jump into the conduction band and the conduction will start. So many semiconductor materials, it can be doped with impurities to alter its conductivity. Okay, so they are doped with impurities for the increase or decrease the conductivity of that the material. So according to the which type of the material is used to fabricate that the MEMS device, according to that the doping concentration is increased or decreased, and according to the doping impurities, the conductivity is also increased or decreased. Then phosphorus P is a common dopant for N-type silicon, and boron is commonly used to produce the P-type silicon. So N-type and P-type, already we have know the basic things. N is nothing but that the which is having the more electrons as compared to the P-type, and P-type having the more number of holes as compared to the N-type. So phosphorus which is having the more than 4 electrons in its valence band. So due to that, after the co-bonding with the Si, it will having that the free electrons which are further move in that the crystal. So that's why there is a large number of electrons are available in a N-type silicon. Then in a P-type material, with the P-type silicon, the boron is added. So boron, which is having that the less number of that the atoms in the last band. So it is having that the whatever that the bonding with the silicon to that the boron, the number of holes the bands are means less number of that the electrons present in the last band of that the boron, so there is the free holes are available for the conduction. So that's why the P-type silicon having that the holes are the majority carriers. So in case of silicon based integrated MEMS devices, single crystal silicon is the primary electronic material, so from which the IC devices are fabricated. Okay. So in case of the silicon based integrated MEMS devices, single crystal SR is primarily electronic material from which the IC devices are fabricated. So we know the IC, that is integrated circuit. These are also nothing but that the over that number of transistors are more. So these ICs are fabricated on the based on the single crystal Si primary electronic material. So this is single crystal silicon. Then next, properties of this single crystalline silicon. So according to that density, according whether it is at the A or B type, the density, that is gram per centimeter cubic, is given, and 2.328 and 2.33, and average is 2.329. So melting point we have to take into the consideration, that is Tm, which is degree Celsius, that is 1420, 1410, and the average we can say 1450. Then Young's model for that is gravitational Pascal, that is 131 and 155.8, so the average is 1.43. Then fracture toughness, so it is 0.9, 0.6, and then the average is 0.75. Then shear modulus, that is 79.9, 64.8, and the average is 72. Then Poisson's ratio, okay, that velocity 0.266, 0.2152, and average of these two 0.240. Then Baker's hardness, that is 1000 for the both the materials, as well as the average is also 1000. Then single crystal silicon looks like this. So already we have seen this type of that the crystalline structures are formed by using allowing the process of the silicon vapor fabrication process. Okay. So see, these are nothing but the single crystal silicon ingots, that is rods, single crystal rods, and slicing, see here, slicing, okay, of these rods, that is single crystal silicon wafer. So this is nothing but the single crystal silicon wafer. Okay, so this is nothing but the single crystal silicon wafer. So today in this session we have seen the how to make that the single crystal silicon wafer. So according to that process, this is nothing but the single crystal silicon rod, and this is nothing but the single crystal wafer. So which we have seen from this side to the this side. Okay, so this is nothing but the output of the single crystal silicons. So thank you. So in this session we have seen that the active or substrate material, from that we have seen the single crystal silicon. Thank you.